Hello, today we'll talk about the stereochemistry at tetrahedral centers. Mostly we'll talk about stereochemistry at carbon. Stereochemistry is is a chemistry about the three-dimensional structure of a molecule around the specific atoms. We are going to introduce handedness first, right? Um, we have two hands, the left hand, right hand. However, the left hands can never be overlapped with the right hand. Even if you try to overlap them, there is no way to overlap it. However, if you look your left hand through a mirror, the mirror image of your left hand will be exactly the same as your right hand. Therefore, your right hand has a mirror image relationship with your left hand. And if if the mirror image of the molecule is not, it cannot be overlapped with the real image, then we say the molecule has handedness. For example, your right hand and left hand has a handedness. Your gloves also has a handedness. Now we are going to apply this concept of handedness to organic molecules, particularly for carbon compounds. Before we talk about the carbon compounds, let's try to focus on the handedness again. Um, the reason you cannot overlap with the right hand with the left hand is because you don't have a plane of symmetry in your hands. If you have a plane of symmetry in your hand, it is very easy to overlap them. But even if you look at your right hand or left hand, you can never find the symmetry plane. So the plane of symmetry is an important concept, whether the object itself is handed has a handedness or not. Now, why do we have to learn this stereochemistry in this chapter? Because a lot of compounds in organic, particularly in biochemistry, has a handedness. And also, the handedness plays a very important role in their function. For example, all amino acids except one has handedness. Most of carbohydrate has a handedness. A lot of proteins made of amino acids also has handedness. Many substrates of enzyme has also handedness. If we now we are going to start more specific terms about the stereochemistry. and we'll introduce the concept of enantiomer. We already talked about the mirror image, right? Now let's try to focus on the carbon compound where you have four substituents around the carbon, but all those four substituents are different each other. Because this carbon is a tetrahedral, we can imagine the three-dimensional structure around the carbon, right? And if substitute, if an atom or atomic groups around the carbon are different each other, then we usually put the asterisks on the carbon here to denote that atom or atomic groups surrounding around the carbon are different each other. Let's take a real example of this kind of compound. Lactic acid is one example. You have a CH3, CHOH, and CO2H. Now, if you look at this carbon, there are several carbons, but just to look at this carbon, all right, then you can immediately tell all four groups are different to each other. In this case, we can think about the mirror image, and also let's think about this compound. And this is OH, COH is COH, CCH3, and COH, COH, and CH, and CH. And this part, in this case, here is CO2H, but here is CH3. In this case, this will be CH3 and the other will be CO2H. Now let's try to overlap them. If you overlap it, okay, you can overlap these two hydrogens. However, you can never overlap these two CH3. They are different. Here is also different. So even if we try to match in other ways, you always find out two atom or atomic groups can be overlapped, but the other two can never. Because there is no way to overlap these two molecules should be different molecule. However, their molecular formula is the same, but they can never be overlapped. So they must be an isomer. And if you look at these two molecules, later on you will notice that these two molecules are in a mirror image relationship, just like your right hand and your left hand. If two molecules are in a mirror image relationship and they can never be overlapped, then we call they are isomers, and this kind of isomers with the mirror images is called enantiomers. If the molecules are not overlapped with the mirror images, then we call that molecule is chiral. Actually, the meaning of this word chiral means having handedness. If a molecule can be overlapped with this mirror image, then we say this molecule is a chiral. So chiral is just the opposite meaning. A chiral is just the opposite to the chiral. Now we have a question. Now we will have a question that why? What is the reason that they can be overlapped with the mirror image, and sometimes they cannot be overlapped with the mirror image? So what is the principle behind that? Actually, the reason molecule can be overlapped with its mirror image is because the molecule itself contains a plane of symmetry inside of the molecules. In that case, they can be overlapped with the mirror image, and molecule will be, of course, a chiral. In other words, if you can never find the plane of symmetry in the molecule, then molecule must be a chiral. Then molecule must be chiral, and in that case, the mirror image of the molecule can never be overlapped with the real image. And a chiral molecule should have handedness. Let's take an example here. This is a flask. This is your left hand. You can immediately tell this is a left hand, right? You know this is not right hand. That means left hand is different from the right hand. But in this case, there is no left-handed flask. There is no right-handed flask. Why is that? Because we can imagine the symmetry plane inside of the molecule. Okay? So if the molecule contains the symmetry plane, definitely the molecule will be a chiral, namely the real image of the molecule will be easily overlapped with the mirror images. If you look at your left hand here, there's no way. This is not right. This is not the symmetric plane. But even if you try to make a symmetric plane in the other way, oh no, that's the upside of your left hand and downside of your left hand, and there is no way to get the plane of symmetry for your left hand. Therefore, your left hand will have handedness, and it's a chiral molecule. If some molecule has a shape like your left hand, definitely will be a chiral molecule. Now, we introduce concept about enantiomer, chirality, and their relationship in terms of the mirror images. Now let's try to apply this concept to a molecule. What is the relationship for the chirality of the molecules containing carbons? For example, let's think about the compound like this. This is a 4-bromodecane. If you look at this carbon, all four substituents, there is one substituent, two hydrogens, and one this. So in this case, there are four atoms or atomic groups, but two of them are the same because two of them are the hydrogens. But in this case, one group, second group, third group, and fourth group. So all the atoms or atomic groups attached to the carbon are different to each other. So in this case, this molecule cannot have the plane of symmetry because this molecule is a three-dimensional structure. It's not plane structure, okay? Because this is tetrahedral. And if you imagine tetrahedral structure of these molecules, there is no way to get the plane of symmetry, including this carbon, okay? So here's one principle. If you have a carbon which has four different groups binding to that carbon, then sure, that carbon provides the chirality, and you will never find the symmetry plane in the molecule under the condition that all four groups attached to the carbon are different. And in this case, this carbon is called chiral center. And chiral center is a carbon atoms. Then we can say chiral carbon. Let's try to look at other compounds, other molecules and predict whether they are chiral molecule or a chiral molecule. Here, in this case, if you look at carbon number 2, 3, 4, 5, 6, of course they are not chiral because you have two hydrogens, they are the same. How about this? Now you have 1, 2, H, CH3, and this part and this part. But in this case, this carbon 6, 5, 4, and this 1, 2, 3, they are the same. Therefore, we can say this molecule is a chiral. And the mirror image of this molecule will be the same molecule as the real image of this molecule. Why? Because you have a symmetric plane. Now, where is the symmetric plane? And this is the symmetric plane because you have this is CH3, H, and if you draw the plane dissecting these molecules, then we can easily imagine one symmetric plane of this molecule. Therefore, this molecule cannot be chiral. Because this molecule cannot be chiral, we can say this molecule does not have an isomer. How about this? It's very similar, but now you have an oxygen here. Now this carbonyl group makes these two different. Because these two different, this cannot be the symmetric plane because the left side is different from the right side. Even if you try other planes, there is no way to find out the symmetric plane because if you look at this carbon here, HCH3, and this part and this part, these two parts are not the same. So all the atoms or atomic groups around the carbon are different. Then we can say this carbon is chiral, and this molecule will have an isomer. And the mirror image of this molecule will not be overlapped with the real image of this molecule. Okay. Now we are going to try to make a connection between physical property of chiral molecules and we're trying to connect some kind of physical property with the chirality of the molecule. Okay. This is a plane polarized light polarimeter. You have a light source here, and this is called the polarizer. Polarizer means if the light is vibrating all directions, but the function of a polarizer is to pass pass the light only vibrating one direction. Okay, so this light pass through this polarizer, then you get only the light which have vibrating these directions, vibrate vertically. And we call this light is a plane polarized, right? And if this plane polarized light pass through the chiral molecules, then this plane polarized light interact with the molecules because the molecule has the bond around the carbon atom is an electron, and the electron will interact with the light. By this interaction, they will change the direction of the vibration of the plane polarized light to the left side or right side, depending on the kind of molecules. In this case, vertically vibrating plane polarized light was rotated to the right side, namely is clockwise. If you have more and more molecules, if you have a lot of molecules, it will be rotated clockwise more and more. So after pass through all this sample if the light passes through all these sample molecules, then the light probably was rotated a lot. Now, here is another polarizer. In this case, this polarizer only passes through the light which is vibrating horizontally. So this polarizer is perpendicular to the other polarizer. We call the other polarizer the analyzer, right? So if you want to see how much this plane polarized light was rotated, then you can just rotate this analyzer until you can see the white light comes out. All right, you rotate this analyzer 0 degree, 1 degree, 10 degree, and then until you see the light pass through this. And if the light pass through, that means the direction of this analyzer for the polarized light is the same as the light after passing through the samples. All right. In that way, you can measure how much of angles were rotated by looking at this the light from this analyzer. Right, here's your eyes. You wait on, you rotate this analyzer. You wait until you see the light signals through this, and then when you rotate it, and then you measure the angle you rotated, and the angle you rotated is an alpha. Now, if you have a lot of molecules, if you have the high concentration of samples, it will be more rotated, all right? So the alpha will be proportional to the concentration of your samples here. Also, if the path length is very long, you have a very long path length, then this light will interact with the molecules more and more, and it will be rotated more. Therefore, this alpha will depend on concentration of your samples and we call path length. All right, this is the length of the sample vessels. Now, why is this? Why? And if you have, if the molecule rotates this plane polarized light, then we say this molecule has an optical activity. Okay. Now, what's the relationship this optical activity and handedness? Actually, if you have a molecule here which has a chiral centers, for example, chiral carbons, then you will see the optical activity. If you don't see any optical activity here, that means your sample is not chiral, okay? So the measuring the optical activity is a very easy and very good way to tell whether your molecule is chiral. Also, then in other words, measuring optical activity is a good way to tell whether your molecule has an enantiomer or not. Now I just introduced optical activity and optical rotation alpha here, and then we are going to define the specific optical rotation. And specific rotation means you divide alpha by path length and concentrations. So specific rotation means rotation divided by path length and concentrations. So specific rotation is unit the rotation by unit path length and unit concentration. Okay, we usually use 10 centimeters of path length. That means the length of this sample vessel. Actually, this is a vessel to you add the your sample through this inlet. You fill this sample vessel with your molecules, all right? So the path length means the length from here to there, right? And also, this is the light source. But if you want to get the consistent result, we have to specify the light for measuring the optical activity, okay? People usually use the wavelengths of 589 nanometers of the light. What is the easy way to get this light? That is to use sodium flame light, and sodium flame light always gives the specific the light with a specific wavelength, and that is 589. And we usually use the D like this. That means you used light source of sodium D line, right? So then, in other words, you use 589 nanometers of the light for measuring optical activity using polarimeters. Let's take an example of the specific example of our compounds. All those compounds, they are very well known. Penicillin, sucrose, camphor, chloroform, cholesterol, morphine, cocaine, acetic acid. All these compounds is natural compounds. Yeah. Chloroform and acetic acid is very simple organic molecules. As you see here, most of the compounds in the living matters or biological samples have alpha D values. That means they are chiral. Actually, almost 100, almost 99, more than 99% of the biomolecules is chiral. That means most of biomolecules has an enantiomers, all right? This is why it is very important to understand the concept of stereochemistry, enantiomer, optical rotation, and the relationship between enantiomer, stereochemistry and their functions. Pasteur is the one who found the enantiomer in the first. He tried to he carried out the experiment with the sodium ammonium tartrate, which has a structure like this. You have two cations, all right? This carboxylate, but you have a sodium here and you have ammonium here. So he has a sodium ammonium tartrate salt. Because this is a salt, it's easy to crystallize it. So he tried to crystallize. He found he found that he has two different shape of crystals, and he separates them. And later on they found two different kind of shape of crystals. They are enantiomers.